I'm Rumka Gill, and today we will be observing the role that Newton's second law plays while analyzing an object in motion. This law allows us to connect the relationship between an object's motion and the forces acting around it. Not only this, but we can predict the velocity and acceleration of an object as well as time moves forward. In this lab, a rolling can of soda on the ground was videotaped and analyzed through Tracker. In this application, we were able to position our object on a set axes and track the location using X and Y coordinates as time moves forward. The right side of the screen displays an automatic chart recording the position of the object at a particular time, as well as graphing these results simultaneously. Because the can was rolling horizontally, the X coordinate position will provide the data for this lab. If we were to flip the axes during orientation, then the Y coordinate would be the variable changing. However, the data should stay about the same. Hence, this experimental data provided us with a graph of the can's position versus time over about 2.07 seconds. The slope of this graph indicates the object's velocity, and because the line is curved, the object was not in constant velocity, and the net force on the object is not zero. To prove this further, we will construct a computational model of a predicted position versus time graph using Newton's second law and basic coding technique. Using GlowScript, we work off a preset code, altering details of our object and its initial conditions. Newton's second law predicts future velocities from the equation final velocity equals initial velocity plus F net divided by mass multiplied by the change in time. We are able to find our initial velocity from our experimental trial, using the first and second points of the graph. Velocity is given by the change in position divided by the change in time. Moving forward, we set the net force on the object to zero, assuming the object should be moving at constant velocity. Finally, we enter the object's mass in kg to complete all components of the equation. After the final velocity equation is correctly implemented, we use the position equation. R final equals R initial plus average velocity, or final velocity, knowing if the object is in constant velocity, multiplied by the change in time. From here, our while loop in the code will repeat these steps over and over until the time limit is over, gathering and plotting the observed results. Using Spreadsheet, we can combine the experimental graph and predicted graph into one, making it easier to compare, or in this case, contrast. The experimental can seems to have an increasing velocity, parting farther from the predicted line as time moves forward. It is conclusive to say that there were definitely net forces acting on the object that the computational model did not account for. Factors of forces may have included friction with the floor, liquid in the can, unleveling of the surface, and more. Newton's second law can only be effective when these net forces are applied in the equation. All in all, this lab put together many concepts, showing the light of how forces can interfere in motion, and how these concepts can be used in equations to predict a future velocity or a future position of an object. Our computational model exemplified Newton's first law, in that it was in uniform motion unless acted on by an outside force. It is clear that the experimental can is exemplifying Newton's second law, and to find an accurate computational model, we would need to inquire on the total net force of the object.